Welcome to the surface of the moon. Today we're collecting lunar soil samples in order to better understand this alien landscape. Except for the fact that I am not on the moon, and this isn't moon dust. However, it's pretty darn close. In fact, it's our most advanced lunar soil simulant ever devised. And today we're going to find out how it was made. First though, I'm going to get out the spacesuit. Scientists and engineers need samples of the lunar landscape in order to perform their experiments. During the Apollo era, astronauts were able to collect 400 kilograms of the stuff and bring it back to Earth. Today it resides in the Houston Lunar Vaults, where it just gathers dust. Why can't we use that? Well, 3 reasons. First, unless you happen to be a very well-funded American researcher, good luck getting your hands on it. Second, you might need a lot more than 400 kilograms, especially if you're creating an entire lunar landscape to drive your buggy through. And third, if you're doing destructive testing, like how to convert moon dust into cheese, then you're very soon going to run out of moon dust. The solution is simulants, something with properties very much like the real thing, without us actually having to go fly to the moon to pick it up. Originally, we thought that there must be some sort of direct equivalent between lunar regolith, that is the rocks and dust that make up the upper portion of the moon's surface, and regular Earth materials. Based on this principle in 1968, PhD student David Carey came up with the first ever lunar regolith simulant. It's a surprisingly soft but also slightly gritty mixture, which he made by combining together beach sand and kaolin clay. Now, David had no idea what the moon was actually made of, but at that point neither did NASA, so the recipe stuck, and they used it to train the Apollo astronauts and test out their equipment. Upon arriving at the moon, we soon realized that the recipe was entirely wrong. The astronauts experienced problems from the get-go. Their equipment didn't function as expected, and its useful lifetime was reduced from months to just hours. It got inside their spacesuits and caused the lunar equivalent of hay fever. Like regular Earth hay fever, just turned up to 11. David's simulant had prepared them for none of that, and by taking a look at a sample underneath the microscope, we can start to appreciate why. David's clay sand mixture has rounded particles, worn smooth by wind and waves. Real moon dust has smaller, finer particles that are also jagged and cruel, like trillions of tiny razor blades. It contained weirder things too, like glass fragments and pure nanoscale iron. First shocked, NASA started to think that if they could understand how the moon was formed and its regolith processed, then perhaps we could replicate that here on Earth to better prepare for future missions. Sure, David might have been disastrously wrong with his lunar simulant, but he did have one useful contribution. His theory that the moon and Earth were made of the same sort of materials was proven correct. Sure, they might look different, but chemically they're nearly identical. This led planetary scientists to develop what's known as the Deep Impact Hypothesis. The early solar system was a very different place. As many as 20 rocky protoplanets orbited the Sun, although they weren't particularly good at it. 4.5 billion years ago, 2 were on a direct collision course. A planet named Theia smashed into the much larger body known as Earth. Molten planet was cast into the void as material from the 2 titanic bodies mixed together. Some fell back to the Earth, but a little got into orbit, forming what we now call the Moon. Over the millennia, this molten moon cooled. Like with the continents of the Earth below, low-dense anthracite crust rich in aluminium and calcium breached the surface to become the lunar highlands. Later, basaltic lava flows made of darker, denser iron components created the Mariner, so named because we once thought that these dark, flat regions were some sort of sea. The solar system remains a dangerous place, and although the Earth is generally quite well protected, occasionally something will sneak through, giving us clues as to what life would be like on the unprotected surface of the moon. This is Barringer Crater in Flagstaff, Arizona. Perhaps one of the least subtle clues is the giant freaking crater. caused by a meteor smashing into the surface, breaking up the rocks, and throwing them out everywhere. Over millions of years of impact upon impact, the lunar regolith gets pulverized to truly tiny grain sizes. And because there's no wind and wave to smooth down the edges, they stay sharp. If you look closely, you can see the beginnings of a mining operation, established here to try mine up the meteoric iron. Unfortunately, that never eventuated, on account of them never actually finding any iron. With really big impact sites such as this one, the material immediately surrounding the impact point will often vaporize, and in this case, apparently so did the meteor. On the Moon, these vaporized products go up, and then the iron components will reform as nanoparticle iron, raining onto the surface. These are much harder to find, but by snooping around craters for long enough, eventually you'll run into this stuff, meteor glass. When the high impact energies of a strike hit something like sand or silicates, it will often melt these, and then when they cool, reforming as glass. I think that's fascinating. I normally think of glass as being a uniquely human invention, so the fact that the heavens will occasionally just give us glass is incredible. Less dramatic perhaps, but by no means less important. High-energy charged particles from cosmic rays and solar winds irradiate the upper layers of regolith. This knocks off an atom here and there, maybe adding an extra one in, and generally weakens the molecular structure. This also results in bands of charged particles which hover over the surface and will electrostatically stick to astronauts and their equipment. As I'm filming, the first crewed missions to the Moon in over 50 years are scheduled for just over a year away. The Artemis missions will take astronauts to the lunar highlands at the South Pole, where we hope to find ample reserves of water ice as well as constant sunlight, the things we need for a permanent colony. In order to prepare, engineers are bulk ordering lunar highland simulant, testing out our equipment. This means demand for it is skyrocketing. Today, I've come to the University of Central Florida to visit Exolith lab and help produce their next batch. Basically, we're bakers of the world's grittiest cheesecake. The formation of the Earth and Moon resulted in a good deal of planetary mixing, which means that we have all of the right constituents for our simulant here on Earth, if you know where to look. They get their bulk ingredients shipped in directly from the source. Anthracite is one of the key minerals, both in Moon regolith as well as Earth soil. However, to get it in its pure form, we need to go to the appropriately named White Mountain in Greenland. Another component is basalt, which comes from the Merriam crater in Arizona. It's just around the corner from Barringer crater, but this one was made by a volcano rather than a meteor, and it has a mine that actually turns a profit. Combining anthracite, basalt, ilmenite, pyroxene, and olivine gets us close enough to the real chemistry. Now that we've got our ingredients, we need to grind them up to just the right diameter. To do that, this is our hammer mill, quite possibly the most terrifying piece of equipment that I've ever seen. Inside there's a steel drum, upon which rests 10 3.5 kilogram hammers. They're made of extra hard steel chromium alloy and spin at 1700 RPM, simulating 3 million years of asteroid impact strikes in 3, 2, 1. In the past, they then take this powder and put it through a number of sieves, with the larger stuff up top and the small stuff at the bottom. You could then recombine this in just the right ratio to get the sort of simulant you were after. However, nowadays, with a whole bunch of fiddling, they've got the hammer mill tuned just right, so that it produces the right distribution, first time, every time. With the ingredients in the correct proportion and ground to the right diameter, we take them and dump them in a cement mix. We mix it for turns of about 2 to 3 minutes and then pause it to scrape down the sides, stopping the anthracite and basalt from clumping too much. We'll have that going for about 15 minutes. Finally, we have baking. This actually involves a number of different steps, and we'll use one, none, or all of them, depending on just how excruciatingly accurate we want our final simulant to be. First up, we have agglutinate. By harnessing the power of the sun in a device that I'm not allowed to show you, we melt down our simulant to form these agglutinate bodies. These then get ground up, providing the nice, fine, sharp glass that we need. Earth minerals contain a lot of water on account of our oceans and atmosphere. Moon minerals don't. So in order to remove this Earth moisture from our simulant, we put it inside a desiccator oven, leaving it there at 200 degrees centigrade for 24 hours. This removes all the water, but be careful, because as soon as you take it back out the oven and expose it to the moist atmosphere, then the water just goes right back in. My favourite baking step, both with a real life cake as well as our simulant, is to chuck it into a particle accelerator. This replicates the high energy collisions of solar wind. So at the end of the day, how good's our simulant? Well, from a chemical and size distribution standpoint, we're pretty much spot on. The raw batter, as it were, is perfect for engineering models and for growing plants in. For dust studies, then an extra fine version is perfect. Wow, those particles are small. Of course, the glutinate version is by far the best and by far the most expensive. Even the blobs look accurate. When you watch the next Artemis mission and humankind once again steps foot on the moon, you can be pretty sure that the astronaut, their boot, and maybe even the entire spaceship spent a good deal of time messing around in simulant much like this. Until then, this has been James Dingley from the Atomic Frontier. Keep looking up.